So first of all, I would like to thank the organizers for the invitation to this conference. I am very honored to give a talk here. Even though when I first received the invitation, I was very nervous because I didn't have anything to talk about. So I had really to work to find something. So I decided finally to talk about some dynamics in Poisson geometry. And so I have a list of small topics that I would like to talk about. Maybe I will list them here. So maybe the first one could be about an invariant of Poisson structures. Maybe a new one for you. Maybe most of you have never heard of it. Which is and maybe it is not exactly new in the dynamical one, but it may be new here for Poisson geometry. It's called entropy of Poisson structure. Of the Poisson structures themselves, without any any vector fields on it. And the second one is about the problem of resonance and non-integrability. I will make some comments about this problem. And the third one, I'm sorry. This is the third one. The second one here first is about local normal form. Of a dynamical system, but when the new feature is that they live in Poisson world, so on Poisson manifold. So the third one is the resonance. The first one is the problem which may be called the reduction commutes with integrability. And maybe you know about reduction commutes with the quantization or whatever, but here is something similar, commutes with integrability. The fifth topic is about what people call Arnold-Liouville. So it's our local action angle variables. So Miner, you should mention also Miner. It's the same theorem, but actually it was Miner who proved it in 1939. But with singularity. And over Poisson, also Poisson. I mean, I add Poisson everywhere. Try to add. And the last one is the problem of bi-Hamiltonian structure, by Poisson, normal form. Of Poisson structure, and for that you need some cohomology, maybe. By Poisson cohomology. I mean, I have only about 50 something minutes, and maybe 6 topics, maybe too much. But so maybe I will mainly talk about the first 3. Why I write 6 here? Because now in the third topic there is a very important work of Dostermann, which inspired what I will talk about. Maybe Raya will talk about Dostermann's work in Poisson geometry, and he will talk about lots of things, but he told me that he will not talk about this resonance so that I can mention it. Okay. And it is maybe less well known than the other things that Raya will talk about, but it is very important. I can assure you that this is something that it is a kind of also very fundamental work of Dostermann, but for Hamiltonian system, and which inspired what I will talk about. Around 83, 84, something like that. Okay. And I want to mention here, maybe I don't have time to talk about these last 3 topics, so I just want to say that there are some other topics. And I write these people name because I would like to, to dedicate this talk to the memory of these 2 great mathematicians who sadly have passed away this year. Vladimir Igorovich Arnold and Hans Dostermann. And they directly influenced many of us. Yeah, right. So I would like to say that I'm dedicated Now, the entropy, maybe. So, what is the entropy? So, entropy, in general, in physics or mathematics, is a concept which somehow measures the degree of complexity of something. So this is the entropy. Entropy. The idea is that it should be related to complexity. Okay, so the main philosophy is that if the system is simple, system or machine or whatever, or simple or regular, okay, in a relative sense, then it should have zero entropy. But you know that in the physical world, maybe zero never happens, or maybe low entropy. Zero or low. And things which are complicated, or chaotic, whatever, then you must have a positive or high entropy. Right? I remember that the Japanese people, they eat food with low entropy. It is better for the hand to eat food, low entropy food. And okay, so mathematically, I think that this notion appeared in information theory by Shannon. By Shannon. I will not have the time to recall all the definitions, but which means the amount of information. So why amount of information related? Because when the system is complex, you need a lot of information to know the state of something. Right? When it's simple, you need just a few information, few bits of information, enough to describe your thing. So that's why actually you can measure it also as the amount of information. That's what Shannon did actually. And then Kolmogorov and then Sinai, who was a student of Kolmogorov, they took over this thing and they adapt it to dynamical system. So and it becomes they call it metric entropy. So measure theoretic actually of dynamical system. And then there is another notion of entropy for dynamical system, which was invented by, I think, Adler and other people whose name I don't remember. And then there was very important work by Bowen and Dinabuk, and so on. And this is called the topological entropy, also of dynamical system. Okay. So this Shannon and Kolmogorov, I think it must be around 1940s and 1950s. So Kolmogorov, I think so. And then topological here is in the late 60s and 70s. Okay. And then more recently, there is a very nice work by Wiese and Langevin and Valsak, something like this, in 1988 in Aplicada Mathematica, where they defined the entropy, which they call it geometric entropy, for regular formulations. Okay, so you have a formulation on a manifold, you can define this entropy. And for example, for codimension one formulation, so it is a geometric, or actually, it depends on the metrics that you put on your manifold. But the fact that it is positive or zero doesn't depend on the metric. So if it's zero, then it stays zero. We change the metric. Okay. So we talk about only zero or non-zero, zero or positive entropy. Then it is an invariant. It's a kind of topological invariant. And for example, if your codimension one formulation has this Gauss-Bion class, which is non-trivial, then it implies that this guy has non-zero entropy, something like that. So it is not, it's related to the topology of the formulation. And then Bis, and Andrei Bis, who is Polish, who defined a similar thing, but for distribution. Okay, and he proved relatively simple, some simple but nice results about the case of distribution. And actually, if you look at all these definitions, they look very similar. And now I give you another definition which also very similar to all those definitions, and actually which will include on this case as special case. I mean, from here, from the topological. Okay. So the definition of entropy. Okay, this is entropy of a geometric structure. Okay. So what do I mean by a geometric structure? So this geometry, so you need some kind of metric. So actually, the setting is as follows: you have a vector bundle A over a manifold. Okay, and then you have a anchor map. Call it anchor map, just a bundle morphism from A to Tm. I told people who know the algebraics, we can recognize that A stands for algebraic, but you don't need the algebraic structure. You just need the anchor map. And a norm on A. Norm on A. When A is finite dimension, doesn't matter what norm, kind of Banach norm. And the entropy will depend on the norm, but the fact that it is zero or positive will not depend on your choice of the norm. Let's just have the norm to define it. Okay. Now you do the following thing: you define a metric. So, like in the definition, you need some metric which grows, or which show exponentially, right? Hopefully, right, with respect to some parameter. So here I define a metric on M like this. So if I have a point X here, first I will define the curves like gamma T. Right? Gamma T is called the A curve, A path. Right? And you know the A path, which means that at every point is equal to the image of some other guy who is in A. Right? So it's project from A. Which starts at X, of course. And I say that this is A path of speed at most R. So the speed. I say that the speed of this curve is at most R. If this guy can be chosen so that the norm is less equal to R. Okay, so it is a path that you can project from A. Okay, you can follow A is a kind of control parameter, control. So you can follow by following A, and with speed at most R. Okay, this is called a path of speed at most R. Okay, so you can go. I mean, like in the dynamical system. Actually, when you have a dynamical system, you have a vector field, you can have this. When example, when you have a vector field X on M, then A is just M times R, and then you have this guy where the norm is, there is a canonical section which project to the, you project A to Tm, so that R here you project to the vector field, to Rx, and the guy whose norm is 1, you project exactly to X. Okay? So a vector field is also a situation like this, a special example of dimension 1, right? So this is more general. And for example, you have a matrix, then of course this guy is just the tangent bundle itself. Or if you have a formulation, this guy is just the tangent bundle to the formulation. Or if you have a Poisson manifold, it is a cotangent algebraic. Right? So that's why it works also for Poisson manifold, because you take A as you take the cotangent algebraic. Okay, so you can define this path, and so entropy it goes away, and then let's call let's call something like P R X. Okay, is on the path starting at X, with starting at X, and speed at most R. Okay, I mean on the A path, the fixed A. Okay. Now we define a new metric from the define. There is no metric for the moment, but I'm sorry. I need a metric here. I need a metric D, a metric on M. Okay, any metric. You just take any regular metric. The entropy does not depend on the metric D. It depends on the norm here, but does not depend on D. And then I define.
When you define the space, you need the path gamma or leaves gamma path?
No. I should look at the paths. I don't need the leaf. I should look at the paths themselves. Okay. Now I define the distance from a point X to a point Y. Okay, on the manifold. So X, Y here are in the manifold. Is equal by the following way: take the super, and then take the infer, and then take the super again. I will explain what does it mean. Of D from gamma X to let's say what's the name of this guy already? Sorry, gamma T X. So it is a curve. Forget X. T here. So sup here is T. This is in the interval 0, 1, and this guy gamma must be in the path on the path which starts at the point Y. Okay, any length doesn't matter, but the gamma must be a path starting at X, but with length at most R. Okay, so what does it mean? You try to get away from Y by a path from X. So the idea is that you have a point X here, Y here. You try to get away from this point Y. Okay, by on this a path from X. But then you try to attract it by the a path starting from Y. So you try to attract it. That's the guy. And then you measure how far they can be away. Maybe it is here, or maybe it is the most far away here. Okay, so it's a kind of the longest distance that you can get away, okay, from Y by a path from X, like that. Then you let Y catch it. Now, but if you define this way, it is not symmetric, of course. So in order to render it symmetric, you just put here plus the same thing, but exchange X with Y. The same thing. Okay, then it will become symmetric. Okay. Well, I already spent a lot of time. Sorry. I have to go very fast. So okay, now you have this dr, which is a metric, a true metric on M. Then you define the, let's say M compact. In the non-compact case, one can modify a bit the definition. I don't have time to enter the detail. You have to localize a bit, take compact subset and so on. And let's call the N epsilon R is the maximum number of so-called epsilon separated points. Separated, so that is dr epsilon separated points in M. So it means that you have M here. You try to put in as many as you can points in M, so that pairwise their distance, dr distance is at most at least epsilon. So they are epsilon separated. Okay. So if you make bounds of like half epsilon, then they don't intersect. So separated by epsilon at least. And then this number in entropy, this number should grow exponentially. So and then you take the log of this number. Grow exponentially with respect to R. Okay? Take the log, divide it by R, and then take the limit. Actually, lim sup usually, right? And then you take R tends to infinity. And then there is epsilon, so you take epsilon tend to 0. And so this is something well defined, and you call it the entropy of A. Is that clear? The definition? Okay, this it measures how this metric grows. I mean, right? How when you let the path lengthen. Now I give you some theorems about this entropy. So, if A is the tangent bundle to a formulation, regular formulation, then the entropy that I just defined is the same as the entropy defined by Giese, Langevin, and Weizsäcker for the formulation. It's the same, exactly the same. So there's nothing new. Actually, I imitated the definition, so there's no surprise. I just modified a bit, not very important. So if A comes from a vector field X, from a vector field X on a manifold, then, not surprisingly, the entropy of A is equal to the entropy of X, the topological entropy of X. Or maybe twice, it depends on the convention. And this is a consequence of this theorem. They show that their definition coincides with topological entropy. Is the consequence. Okay? Now, if A is just a distribution, a regular distribution on M, then the entropy of A is the same as entropy defined by Bies, Andre Bies for the distribution. Very not surprising. Actually, Bies showed that these two, that his definition, okay, it's not surprising. It shows that you recover the old definitions of entropy in the old case. Okay, so what can be new here? Right? The new thing is that we can apply this definition to, say, singular formulations or Poisson structures. Right? And it gives a kind of invariant for the Poisson structures. Now, okay, maybe I have to show you some results concerning Poisson structures. Oh, but first, maybe another theorem. If the map, the anchor map, is surjective, then the entropy is 0. Okay, so it means that in particular for symplectic manifolds, the entropy is 0. Okay, so H symplectic is 0. Now I have something different. So let's say that A is equal to D. It's a distribution, a regular distribution, which satisfies the so-called bracket generating condition. Bracket generating. It means that you take brackets of the vector field which are tangent to D, and if you take enough time, that it generates the whole tangent space. And in control theory, if you have a bracket generating distribution, that then you can control, so you can go from any point to any other point by the advance. Okay? Then if you have such a thing, then the entropy is also 0. So it means that for controllable systems, entropy is 0. So here, in order to have non-zero entropy, you need something which cannot be controlled by in this sense. And by the way, the case D is contact was proved by Bies. So Bies he proved it for the case when, particularly when it's contact. So of course contact is bracket generating, but then I observed that it's true in this modularity. And to prove it, one can use the so-called bond-box theorem in Riemann geometry. So use it then. I have almost half an hour plus. Now, as regards Poisson manifold, I want to show you some example of positive entropy, right? So let's say if you take a manifold which is something like this times R or T, so times something one-dimensional, here you have a vector field x, and here you have the vector field d over dt. So vector field, regular vector field on this line. Okay, then the entropy of this Poisson structure is positive if and only if, actually, if we really make a good norm, then we can show that it's equal. Or maybe I can write it after choosing a good norm, exactly equal to the entropy of x. So in order to create an example of positive entropy, Poisson structure positive entropy, you just take a vector field of positive entropy, and there are many of them. People in dynamical system know how to create them. Hyperbolic system have positive entropy. And this Poisson structure is regular. You can take x regular and also integrable in the sense of symplectic groupoids. Now, another thing is that the entropy of G star, where G is linear Poisson structure, is always 0. So this is something non-linear. Okay, so so the remark is that here, so you see that this is a kind of interesting environment I think worth looking at, and it is different from the integrability. So we can have integrable Poisson manifold with 0 entropy and non-integrable Poisson manifold with positive entropy. So integrability is also kind of, but in general, the idea is that Poisson manifolds that we get from mechanics. So you study mechanical system. First you start with the symplectic manifold, you do reduction constraint and so on. But if those reduction constraints are nice, then you should end up always with something with 0 entropy. So in mechanical system, you don't want something, something that you can calculate. You don't want something of positive entropy. You will generally end up with something of 0 entropy. So if you have a symplectic manifold, and let's say you do reduction, then it is still 0. Right. Proper action. Yeah. Maybe it is not. Maybe it is not 0. The idea is that in general integrable system have 0 entropy. It is not always true because of decisional singularity. But if it is no decision, then it should be 0. Okay, so maybe it just on maybe another theorem. Well, whatever I write as a theorem here, if they look new, then they are, let's say, theorem inside quotient marks because they are not verified by anyone else than myself. So maybe the 90% true. That if you have full set of Casimir, good Casimir, then the entropy is 0. Okay. So I mean, so really for entropy to be positive, it must be somehow the leaf structure is complicated. Okay, but I already spent half an hour, sorry, and I still have 5 topics. Okay, now I will pass quickly to the normal form so that I can talk about Dostermatt. Just something that I really want to talk about is Dostermatt, very beautiful work. I just want to try to explain a bit. But first I must mention about the normal form before talking about Dostermatt. So normal form of Hamiltonian system. So you know that when this is a very old work going back to Birkhoff and Poincaré and Dulac and so on, that if you have a Hamiltonian system on a symplectic manifold which vanish as a point, okay, then you can write as H2 plus H3, so on. It is just a Taylor expansion at 0. And H2, if it is not semi-simple, you can write as semi-simple plus nilpotent, because the algebra is SP2N actually of these quadratic functions under the Poisson bracket. And now Birkhoff says that you can always change the coordinates so that there always exists a coordinate system such that H commutes with HSS, with H2SS. Yes. Okay, and then it is called the normal form. So you can write it in such a way that it commutes with each other. And it means that when you look at the terms here, lot of terms will vanish. Only terms which are called resonant can remain in this normal form. Okay. Unfortunately, this one is only formal in general. So in general, you can have a form and change of coordinate which diverge in general, which need not converge. However, there is a theorem which says that if H is analytically integrable, I don't have time to define what does it mean, then this is the analytic normalization. You can make it analytic if it is integrable. Okay. Now, there is I have to define what is the resonance here. And this theorem that I just mentioned is due to Wei in the non-resonant case and to Ito and Meisem in the resonant case. Well, so now resonance, because it will come to Gauss-Selmer. So you look at HSS, you can always write it in this way. The sum of, say, pi square, let's say gamma I, pi square plus qi square, okay? Maybe over 2, it depends on the convention. And now this gamma I call it the frequency of the system, known as a sum of harmonic oscillators. Then you take this abelian group, because they are numbers, okay? These numbers they are numbers, complex numbers, you know. You take this group, okay? Generated by this abelian group. So it lives in C, but it's a subgroup of C. But so you look at the rank of it. This is a free abelian group. The rank of this group is called the toric degree of the system at the point 0. And here let's say I is from 1 to n. And n, let's call it R. Minus R is called the degree of resonance. So here is our resonance. This is the degree of resonance. Okay. So if these numbers are commensurable, how to say, over Z, then you say that there is a resonance. Now, if there is no resonance, so it means that the I is equal to n. So for non-resonant, if the system is non-resonant, then actually the normal form says that H can be written as a function of P1 square plus Q1 square and so on, Pn square plus Qn square. So this can be reduced to a function of n variables instead of 2n variables. So here have only n variables, this variable. And then it is integrable. So the first integrand are Pi square plus Qi square, they are the first integral. Okay? So generic Hamiltonian is non-resonant and is formally integrable. That's what the Birkhoff theorem says. Now what about the resonant case? Actually, let's call this degree of resonance D. Resonant case. Again, so if D equal to 0, then it is integrable. If D is equal to 1, and it is still integrable. Why? Because we cannot write it this way now, but just still n minus 1 quadratic first integral instead of n. Here we have n. When actually the number of quadratic integrals is the toric degree. Okay? We have n minus 1. But then remember that we have h is same as the first integral. So in total we still have n, even though there is 1 degree of resonance. Now, in order to have something non-integrable, you need at least 2 resonances. Right? At least the double resonance. And maybe then it is non-integrable. Right? So it was a question which was open for a long time, I think. And it was Deutsch-Zermatt who first actually show that it is the case. Okay, so Dosterman's style is that he did it, actually his story is very general, but he did it on a very concrete example. And actually his methods can be applied in a much more general situation. So Dosterman. And his proof is at the same time very geometric, and also he used very well complex analysis also. But his proof is with a lot of geometric intuition. So that was proof of the thing. Let's say n, let's say h on at six-dimensional manifold. H is p1 square plus q1 square plus p2 plus q2 square plus 2 times p3 square plus q3 square, and then plus higher order term. Okay, I should write h3 and then plus so on. This is h2. So you see that there's a double resonance here. So the case when d is equal to 2, we need at least e equal to 2, and it's called 1, 1, 2 resonance. And so 1, 1, 2. Okay. Now he proves the thing. First, we can always like h3. There is a coordinate system. There's a linear change of coordinates, so that h3 can be normalized further a bit. I don't remember the exact formula. I have to look at my notes. Can be written like this: q3 times beta 1 q1 square minus p1 square plus beta 2 q2 square minus p2 square, and then plus p2 p3 beta 1 p1 q1 plus beta 2 p2 q2. So it is a third degree homogeneous polynomial which can be written like that, where beta 1 beta 2 are numbers, constants. Okay, so he look at the real Hamiltonian, so that's why these numbers are real. Now he shows the following thing: theorem of Dosterman. In 84, and 83, 84, I think. He mentioned already in 83 that if beta 1 greater than, strictly greater than beta 2, strictly positive, then there is no other first integral independent of h and h2. Of course, any first integral will compute with h and h2, and h and h2 are the two first integrals. But here the system has 3 degrees of freedom. You need another integral in order to be integrable. And she says that there is no other integral independent. So it means that any integral that you can find will be a function of those two guys. Okay, so it is not integrable. And actually, he looked more into the dynamic, you see something like horseshoes actually. So it's really not integrable. And actually, the statement is stronger. It said no formal first integral. So the system is not formal integrable. Okay. Now, just a few words about the proof. The proof is very beautiful, but I think that one would need half an hour to explain it. But I just mentioned how he managed to prove this thing. Very beautiful. So he looks at H3 equals 0. This surface, this is 5-dimensional thing. Let's call it Q5. Yeah. Okay. Now he shows the following thing: that almost all orbits of H2. So actually, if Actually, in order to show this, it is reduced to showing that H2 doesn't have any first integral. One independent of itself and and of H3. Sorry, H3 doesn't have any first integral, independent of H2 and itself. So of H3 on this guy are periodic. So this is a very geometric statement. All the orbits are periodic except a family of heteroclinic orbits. Okay, so something like this. And now, you see that heteroclinic orbit, it goes from one point to another point, and it takes infinite time, right? The time to go from one point to another is infinite time. Now, just look at the orbits which are periodic, but which are close to this guy. Okay, it's, I don't know, but something like this, right? Not exact, but let's say this is periodic, but close to this heteroclinic. Then what happens is that the period, the time to make the circle must tend to infinity, because in the end it ends here. Okay, so the period goes to infinity when you approach some point on when you approach this heteroclinic orbit. All right. Now, actually, you take the period function. P is the period function. Okay. Now, this function is a first integral. It's clear because it remains on the orbit. It is independent of H2 and H3, which is easy to see. So you have a complete set of first integral, actually. Something like this, almost. Okay, I skip some detail, but you see you have three integrals. So if there is any other integral, then it must depend on these three guys, because at most you have three. Right? And now, the point is that this guy is not analytic. It goes to infinity. And actually, it has infinite branching near the zero. So it means that the level set, they twist like this infinitely many times. Not only the function is analytic, but the level sets are not analytic. Okay? That's why, if you have some function which is analytic and which depends on these three guys, it cannot depend on this guy. Because if it really depends on this guy, the level set wouldn't be twisting infinitely many times. It is impossible for an analytic function. And that's why it depends only on these two guys. And that's basically the idea of the proof. But so it's very geometric. Okay. So that's it. And after those semesters, of course, there are many people who study similar problem and showed similar thing. And actually, I want to mention to you something. So you see that if you have a dynamical system which has the first integral and local, okay, near the point where it is zero. So at one hand you have first integral. Okay, so if the vector field preserves first integral, let's say you take it is linear parts and it preserves the homogeneous part here. Okay, and because the linear vector field preserves some homogeneous function, then it implies that the eigenvalues must satisfy some resonance relation, because it preserves some homogeneous function. So actually, first integral implies resonance. Right? You see? But on the other hand, when you have resonance, then most of the time, if you don't know a priori that you have first integral, you just know that you have resonance, then what the resonance implies usually is non-existent of first integral. This is quite funny, right? I mean, this is a hate-love situation, relationship. Something like this. But actually, it is very difficult to be integrable. You need an exact balance between resonance and first integrable. You have too many resonance and too few integrants, it's not integrable. But I just told Tudor before she stopped that I have a meta theorem which says that 1/5 of dynamical systems in the world are integrable. 1/5. You know that if you look at the integrable systems are very rare, few in between because very special parameters, already from the time of Poincaré and so on, very few parameters. Like rigid body, there are very few integrable systems. But why there are 1/5 of systems in the world which 1/5 are integral? Because actually integrable systems, they are very persistent. So other systems like chaotic, they explode, they disappear after a short time. Why integrable systems or perturbation, they persist like forever. And that's why in practice we see lots and lots of integrable systems because they are persisting. So they compensate for the rarity by longevity. And why 1/5? Well, I will tell you later. But really many systems. I mean, even though there are few integrable systems, they are really a very important class of systems because those are systems that are most easily observable in the world. Now, okay, so inspired by Dostomat, now I want to do the same thing, but for Poisson manifold. So normal forms and resonance in the Poisson world. I should have 10 minutes. So the question is that what is the analog of Birkhoff normal form, but for Hamiltonian system on the Poisson manifold? Well, I don't want to take any Poisson manifold. I want to take a Poisson manifold which is nice, which is not symmetric, but nevertheless, which comes from dynamics, which comes from some reduction. So you know that when you do some reduction, especially when the group is compact, right? Then basically, locally, the Poisson manifold will look like this. It looks like a symplectic manifold. First, we have splitting theorem by Alan, and then the transversal part will look like a Lie algebra, actually. It can be linearized. As this, where G is reductive. But if it is nice, then it looks like this. So I'm mainly interested in this situation, and actually we did work with Philippe Monnier and myself. We published a paper in 2006 about normal forms of Hamiltonian bicycle insertion situation. Okay. Now, to simplify, I will forget about this case where it is non-zero. So I will look only at this case, even though in our paper we did the general case. So here you write H. So H again. H is on G star. So as usual is H1 plus 1. Okay. Now the thing is that theorem with Monnier, with Philippe, says that actually you can transform the coordinate system in such a way that G star remains G star. It means that you don't change the Poisson structure. You change just the function. And the function will be in such a way that it comes with some H1. Where H1 is a generator of the semi-simple part of its linear part. Okay, H1. And this H1 is linear function. Actually, here you see that in the case when the Poisson structure vanishes, that H doesn't have to have zero differential at zero. Right? Also for linear functions, the vector field vanish because the Poisson structure vanish. Right? It can start with the linear part. So you can write H as H1 plus 1. It doesn't have to the linear part doesn't have to vanish for the vector field to vanish. Right? And actually this H1 is in the Katang algebra in G. This H1, the semi-simple part, which we can normalize, so we can put it in such a way, is very similar to Birkhoff, but instead of SP, SP2N, Katang in SP2N, we have Katang in G itself. Okay? Now, the generic case, what is the generic case? Generic case means that H1 in T generic. Okay? And it means that And you know, in T there is this lattice, so it avoids the lattice somehow. You write this in terms of vector field of the lattice, and the coefficients, they are not commensurable, something like that, similar to the user. So generic, then actually I talk about the torus degree. Here's a similar thing. Then the torus degree of this guy is equal exactly. No, okay, I will write this way. Then H actually commutes with the whole T. Not only with H1, but with the whole T. Okay? Now, when it commutes with the whole T, then you have n plus 1 first integral. You see? So, let's say the rank of T is n. So, T gives you n first integral. Of course, they are katang, so it's a katang separation, so the elements, they commute with each other. So, I have here n first integral plus 1 for H. So you have first integral, n plus 1 first integral. Right? So for example, if G is something like SU3, then you see that the symplectic leaf, the rank, right? The dimension of the symplectic leaf is 6, if I'm not mistaken, 6. And then you have n is 2, so the rank of the Lie algebra is 2. And then you have 2 plus 1 is 3, so we have 3 first integral or something 6-dimensional. So actually, in the SU3 case, the Poisson, the Hamiltonian dynamical system is always formally integrable. Okay, so this is only formal. It's formal in general and analytic. We can make it analytic if integrable. Analytic. Okay. Now, what happens if G is big, very big? Then you see that this number, n plus 1, is much lower than the symplectic dimension of the leaves. And the dimension of symplectic, for example, if you take SU4, right? Then the symplectic leaves have 12 dimensions. You need 6 integrals. And n plus 1 is only 4, so you lack 2. Okay? So it means that in general it should not be integrable. Because you don't have any other integral. Oh, because you don't know, you don't find other integral. And actually the theorem is that you don't have any other integral. That's what I want to say. Theorem. If H1 generic and H2 also generic. So H is equal to H1. H1 doesn't matter actually. Generic is in T. And like Dr. Matt, you want to look at the next term and you want it to be generic. Okay? I don't want to define it. What does it mean? Then there is no other first integral independent of what? Of the obvious ones that you know. So of the Lie algebra of the Katang algebra T, which is you on the first integral of H, because it commutes with T, and of H is same, and of the Casimir one. Of Casimir don't count as first integral because they vanish on symplectic. They are constant. But so it means that there is no other first integral, so the CM is formal, non-integral. So it means that it is formally non-integral. Okay. So that's the main theorem actually that I want to mention today. And I have no time. I just mentioned how to prove it. When you know, Dr. Marty proved it with Spatial solution. You see that these are Spatial solution. You look near Spatial solution, and actually, when you look at the proof, it reminds very much the old methods of, let's say, Poincaré or Kovalevsky. They also look at Spatial solution. Then the branching, and the branching is bad. Then there is no first integral. Here it's very similar. So in this case, the proof goes in a similar way. You look at Spatial solutions, which is actually the so here, G star, here there is T star, and this is T. And this guy asked question solution. Actually, the system vanished there. There's just fixed point. And then we look at the local normalization here, and then, well, I don't have time to enter the detail. But also in this same philosophy, and they use also use Birkhoff normal forms format to prove it. Okay. So I have just 2 minutes left, and I don't have time to talk about the other 3 topics, but I just want to mention that Agnon-Lewin is something I like very much. Agnon-Lewin minor actually, and my thesis, which date back to 1994, actually was about this problem, and then there's some further development, and so in the Poisson case, and recently there is a work of Eva Miranda, and Paul Vahek, and Camille Laurent, who also did kind of Agnon-Lewin for Poisson structure, and I think we can further generalize this. And that's it. I just want to mention Eva. Yeah, okay. So that's it. Thank you very much.